How can we determine the performance of a solar cell? Or, in other words, how much of the energy in the solar spectrum can be converted into electrical energy? This is the first important question which will be addressed this week. First, in this block I will present a simple electrical circuit and corresponding current voltage curves which are able to describe the behavior and the performance of solar cells under illumination and under voltage bias, as we have discussed in the detail last week. Before I do that, I will quickly summarize last week's important highlights concerning the physical working principle of a solar cell. Last week we have shown that we can dope semiconductor materials N-type and P-type. In P-type, the holes are the majority charge carriers, and in N-type, the electrons are the majority charge carriers. If we have semiconductors in which one part is doped P-type and another part is doped N-type, we have created a so-called p-n junction. We have also seen that two different mechanisms control the transport of charge carriers in semiconductors: diffusion and drift. Diffusion is controlled by a density gradient, whereas drift is controlled by electric fields, which you can build in the p-n junction or apply externally. In a p-n junction, the diffusion of majority charge carriers through the p-n interface followed by recombination creates a space charge region or depletion zone at the p-n interface. In the dark and in thermal equilibrium, drift of minority charge carriers and diffusion of majority charge carriers are in balance. If we apply a reverse bias on such p-n junction in the dark, the depletion zone gets wider. The diffusion of majority charge carriers is suppressed and only an extreme small current related to drift of minority charge carriers is generated. If we apply a forward bias on such p-n junction in the dark, the width of the depletion zone is getting smaller. The diffusion of the majority charge carriers is significantly enhanced and overrules the drift of minority charge carriers. The p-n junction becomes conductive and is able to generate a current. If we illuminate the p-n junction, the density of the minority charge carriers is increased many orders of magnitude, and as a result, the drift becomes dominant and the p-n junction generates a large current. Now we are going to construct first an equivalent circuit in which we can describe the behavior of a p-n junction solar cell. We have discussed that in the dark a p-n junction behaves like a diode. A diode is an electrical element that if you apply a forward bias on it, it becomes conductive in one direction. Whereas if you apply a reverse bias on it, a diode is hardly conductive and basically blocks the current in the opposite direction. p-n diodes are electrical elements used in many electrical circuits, and their main function is to allow an electrical current in one direction and block an electrical current in the other direction. A p-n junction is represented by the electrical symbol shown here. It's a triangle with on top of its vertex a line. The triangle points in the direction in which the diode allows an electrical current to flow under forward bias condition. In the opposite direction, the diode blocks the current. So now we put the p-n junction in the dark and apply a reverse bias. The p-n junction generates an extreme small current in the block direction of the diode. The current direction in electrical circuits in general points in the direction in which the positive charges flow. It means that the electrons, which are negatively charged, flow in the opposite direction of the current direction. This implies that under reverse bias, the extreme small current in the block direction can be represented by electrons moving in the direction of the triangle. Now we consider a p-n junction in the dark under forward bias. The p-n junction generates a significant current in the forward direction of the diode. As current direction is defined in the direction of the flow of positive charge, it means that under forward bias the electrons responsible for the current flow in the block direction of the diode. Note that the current on the forward bias is opposite and much higher than on the reverse bias. The relation between current and voltage of a PN junction can be illustrated in a so-called IV curve. The vertical axis corresponds to the current of the PN diode, and the horizontal axis represents the voltage applied over the PN diode. A negative voltage, reflected by the gray area in the IV plot, corresponds to reverse bias voltages. As we can see, the current is close to zero. Applying a positive voltage, reflected by the light yellow area, corresponds to the forward bias. Above a certain voltage, the current starts to significantly increase with increasing the voltage. This is a characteristic IV curve of an ideal silicon PN junction in the dark. This IV curve can be described by a relatively simple expression which shows that the relation between current and voltage is an exponential function. The I stands for the current at a given voltage V. Q is the elementary charge of the electron, Kb is the Boltzmann constant, and T is the temperature of the PN diode. I0 is the extreme small current in the block direction under reverse bias conditions. This current is very often referred to as the leakage current of a PN junction. We won't derive why the current and voltage are related by this exponential expression. You only have to know for the moment that the IV curve of a PN junction in the dark can be described by this expression. If we put a very large negative voltage into this equation, you can easily see that the exponential term becomes zero and the current is equal to the small leakage current I0 close to zero. If we apply a large positive voltage, we see that we get a large positive current and the exponential term dominates over the -1 term in the equation. Note that the current on the vertical axis is positive if the current flows in the forward direction of the diode, whereas it is negative if it flows in the block direction of the diode. Now we will illuminate the PN junction using light. It means that we are going to generate a large current dominated by the drift of the minority charge carriers, which is opposite to the forward direction of the PN diode. This is represented in the equivalent circuit by a current source which is connected in parallel with the diode. The electrical symbol of a current source is a circle with an arrow. The arrow points in the direction of the positive current. It means that the far majority of the electrons in this equivalent circuit travel through the current source in the opposite direction of the arrow. The current generated by the light is IPH, where pH stands for photo. Note that the photocurrent is in the opposite direction of the forward current of the diode. Now we look to the IV curve again. The red line corresponds to the IV curve of the diode in the dark. Adding the photocurrent, the typical IV curve of the diode shifts down the vertical axis in the direction of negative currents in reference to the forward bias direction of the diode. This circuit is the circuit for an ideal solar cell. This means that we have not included all types of electrical and optical losses. We will come back to that later this week. The IV curve of an ideal solar cell can be described by a simple equation. The total current generated by an illuminated PN junction is the photocurrent minus the current of the PN diode in the dark. In the equation so far, we have used current I, which has the unit ampere. This is sometimes not the most convenient unit to express the electrical response of a solar cell to light. If you would increase the area of a solar cell, it means that the total current of the solar cell is increasing as well. So the current depends on the area. In the lab, researchers like to use the unit current density J. This is the current generated per area. The advantage of this unit is that you can compare different solar cell technologies, as not every technology generates the same amount of current per square meter. If we assume that A is the area of a solar cell, the current density J is equal to the current I divided by the area A. So the current density is expressed in ampere per square centimeter or amperes per square meters. As you see, the vertical axis of the current voltage plots are already expressed in current density. From this point on, we won't talk about IV curves, but we will talk about JV curves. So from now on, we will use current density. Summarized, I have introduced an electrical circuit and simple expression which describes the behavior of a PN junction solar cell under voltage biasing and illumination. This behavior can be represented in a so-called JV curve. How does this JV curve relate to the performance of a solar cell? Or in other words, the conversion efficiency of light energy into electrical power? I will answer this question in the next block. How can we determine the performance of a solar cell? In the previous block, we have introduced the JV curve of an ideal solar cell and its corresponding electrical circuit. In this block, we are going to discuss the external parameters that determine the light to electricity conversion efficiency of an ideal solar cell. Let's consider that the terminals of an illuminated solar cell are not connected. This situation is called an open circuit. In open circuit, the solar cell does not produce any current and solely produces a voltage. This voltage is called the open circuit voltage. The voltage is easily recognized in the JV plot by the intersection of the JV curve with the horizontal axis corresponding to a current density equal to 0. We can derive a simple equation for the open circuit voltage of an ideal solar cell. In the previous block, we have derived a simple equation for the current density which had two components: the photocurrent generated by the light-excited charge carriers and the typical JV characteristic of a diode in the dark. Under open circuit conditions, the current density J is equal to 0. If we solve this equation, we arrive at a simple expression for the open circuit voltage. It's linear with the Boltzmann constant times the temperature divided by the charge of an electron. And it's linear with the natural logarithm of the ratio between the photocurrent and the leakage currents of a diode plus 1. Note that in textbook the first term also contains a diode ideality factor n. This factor reflects to which extent the JV curve can be described by the behavior of an ideal diode. For the moment, we have assumed that the recombination occurs in the bulk through defect traps in the band gap, the so-called Shockley-Read-Hall recombination, and that the recombination is limited by the minority charge carriers. In that case, the ideality factor is equal to 1. However, if the recombination occurs, for instance, at interfaces, or is limited by both charge carriers, or is determined by Auger recombination, this factor differs from 1. However, during this course, we consider the situation that the ideality factor is equal to 1. The equation shows that the open circuit voltage depends on several parameters. First, the equation shows that if the photocurrent density is increased, the open circuit voltage is increased as well. This means that by increasing the irradiance, or in other words, by shining more light on the solar cell, the open circuit voltage can be increased. Secondly, the open circuit voltage depends on the temperature. Although this equation on first eye suggests that the open circuit voltage increases with temperature, this is not the case. The leakage currents J0 of the diode strongly depends on temperature. The higher the temperature, the larger the leakage current and the smaller the open circuit voltage will be. The open circuit voltage depends on other factors as well, such as the band gap of the absorber material, the amount of doping of the dope layers, and the quality of the material, or in other words, the defect density. We will come back to these relations later during the course. If we short circuit both terminals of the solar cell, the illuminated solar cell will solely produce a current and will produce no voltage. This current density is called the short circuit current density. The short circuit current density can easily be recognized in the GV curve as well. It's the intersection between the vertical line corresponding to zero voltage and the JV curve. We can derive a simple equation for the short circuit current density of an ideal solar cell, using again the expression of the JV relation. If we take a voltage equal to zero, the short circuit current density is equal to the photocurrent density. The short circuit current density depends on several factors like the incident light intensity, the spectrum of the incident light, the optical properties, and the collection probability. Now we like to know how much power a solar cell can deliver and how power is related to the JV curve. As you might know from your physics class, the power is equal to the current times the voltage. The unit for power is watt, and therefore is equal to ampere voltage. However, since we use current density in the GV curves, we will talk about power density, which is power per area. So current density is expressed in amps per square meters or milliamps per square centimeters, which means that the power density is expressed in watt per square meters or milliwatts per square centimeters. We have added the power density in the GV curve as a function of the voltage using the green curve. The vertical axis on the right shows the scale of power density. Note that if the power density on the scale is negative, it means that the solar cell is generating power, whereas if the power density is positive, it means that the solar cell is consuming or dissipating power. The green curve shows that the power density is varying with the voltage, and it shows that the power density has a maximum. On the GV curve, this point is called the maximum power point, and the power density generated at this point on the green line is P max. The graph demonstrates that if the solar cell is in open circuit, which means it's only producing the open circuit voltage and no current density, the power density is equal to zero. When the solar cell is in short circuit, which means it only produces a current density and no voltage, the power density is equal to zero as well. If the voltage is smaller than 0 volt, which we call reverse bias, the illuminated solar cell does not generate power but consumes power. Basically, an illuminated solar cell under reverse bias will heat up. If the voltage is larger than the open circuit voltage, the illuminated solar cell is dissipating power as well, and the solar cell will heat up as well. The solar cell will have its best performance in its maximum power point. The voltage at the maximum power point is called VMP, and the current at the maximum power point is called JMP. Which means that the maximum power density, Pmax, is equal to VMP times GMP. With other words, the shaded area under the maximum power point in a JV plot represents the power density generated. Now we introduce the external parameter fill factor. The fill factor is the ratio between the maximum power and the product of the short circuit density and the open circuit voltage. Or the ratio between the product of the maximum power point current density and the voltage and the product of the short circuit density and the open circuit voltage. The fill factor can be easily visualized in a JV curve. Basically, the fill factor is the ratio between the area shaded red-yellow and the red area. With other words, the fill factor is the ratio between the rectangle with sides VMP and JMP and the area with the sides of the open circuit voltage and the open circuit current density. This means that we can express the maximum power density as a product of the fill factor, the open circuit voltage and the short circuit density. It implies that it is impossible for a solar cell to have a fill factor equal to 1. In that case, the JV curve should have the shape of a rectangle. In the homework of this week, we have an exercise in which you have to derive a relation between the fill factor and the open circuit voltage of an ideal solar cell. This expression will show that the larger the open circuit voltage, the closer the fill factor will be to the value of 1. Now we introduce the conversion efficiency eta of a solar cell. This is the ratio between power density coming out of the solar cell, P out, and the light power density of the light incident on the solar cell, or in other words, going into the solar cell, P in. The conversion efficiency of solar cells are defined in its maximum power point, so P out equals P max. P max, as discussed, equals the product of GMP and VMP. This product equals to the product of the short circuit current density, the open circuit voltage, and the fill factor. As a result, the conversion efficiency can be expressed in the external parameters of the solar cell, the open circuit voltage, the short circuit current density, and the fill factor. To be able to compare the efficiencies of different solar cells, the so-called standard test conditions have been introduced. The standard test conditions describe the conditions for P in and the temperature of the solar cell during the GV measurement. The temperature of solar cells on the standard test condition is determined to be 25 degrees Celsius. The solar spectrum has the spectral shape of AM 1.5 and a total irradiance of 1000 watts per square meters. As a reminder, a typical solar spectrum with the shape of air mass 1.5 is shown here. On the left vertical axis, we show the spectral power density. The irradiance on the standard test condition has to be equal to 1000 watts per square meters and is given on the right axis. The blue line represents the irradiance and equals the area under the spectral power density up to the wavelength lambda. As illustrated, if we integrate over the entire spectral power density, the blue line, corresponding to the irradiation, equals 1000 watts per square meters. Note that 1000 watts per square meters equals 100 milliwatts per square centimeters. Let's get a feeling of typical values. Let's look at this example of a JV curve and assume that it has been measured under standard test conditions. The JV curve represents a typical value for crystalline silicon-based solar cells. The maximum power density is 19 milliwatts per square centimeter, which means under standard irradiance of 100 milliwatts per square centimeters, the conversion efficiency is 19%. If we consider the open circuit voltage of 0.64 volts and the short circuit current density of 35 milliamps per square centimeters, we arrive at a fill factor of 84.8%. We have introduced the external parameters of an ideal solar cell. In the next block, we will show a video clip on how a real JV measurement of a solar cell in the Delft Solar Lab is performed. We will see that the JV curve of the solar cells and solar panels in reality do not perfectly match the JV curve of an ideal solar cell. What is the origin of all these non-idealities? I will answer this question in the next block. We are going to measure the efficiency of a solar panel. We do this by measuring the JV curve and its external parameters as discussed in the previous block. How does such experimental setup look like? It consists of several components. The first component is a solar simulator, which is a light source that simulates both the shape of the AM 1.5 solar spectrum and an irradiance of 1000 watts per square meters. Secondly, the setup has a voltage source which applies a varying voltage over the solar cell or solar panel. An ampere meter measures the current generated by the solar device at every voltage. Finally, a temperature-controlled substrate guarantees that the solar cell is at the required standard temperature of 25 degrees Celsius. Let's see how such measurement in reality works. For that, we will go to the Delft Solar Lab. Here you see the voltage supply and the ampere meter. Typical panel areas are in the range of 1.5 square meters. This means that you need a light source with a spectrum shape and irradiance which is homogeneously distributed over large areas. In the solar lab, we use a large AAA solar simulator from Eternal Sun. AAA indicates that the spectral match, the uniformity and the stability is of A-class quality. The crystalline silicon solar panel needs to be connected to the voltage supply and the ampere meter. In addition, a thermocouple is connected to the panel to monitor the temperature of the panel during the JV measurements. Without additional temperature control, the solar panel will heat up in time. Here we demonstrate that the panel is at a required 25 degrees Celsius using a Fluke infrared thermometer before the panel is moved under the solar simulator. A software program controls the JV measurement. The voltage over the panel is varied while the current is measured. On the screen, the resulting JV curve and power density is plotted from 0 volts up to the open circuit voltage. As the setup measures the total current of the panel, the active area of the panel is an input parameter for the software. Using the given active area, the software calculates the current density of the panel. In this example, the maximum power density is 17.4 milliwatts per square centimeters, which corresponds to a panel conversion efficiency of 17.4%. The JV curve measured does not perfectly match the JV curve of an ideal solar cell. In reality, a solar cell can have additional electrical losses. These losses can be represented as parasitic resistances in the electrical circuit in addition to a non-ideal solar cell. Here we will discuss two important resistances, the series and the shunt resistance. The first resistance is called series resistance. Several effects can be the origin of a series resistance in a solar cell. Let's consider a standard crystalline silicon solar cell, which we will discuss in great detail next week. First, the current moving through the semiconductor materials of the p-n junction can experience a resistance. Secondly, the interface between the semiconductor material and the metal contacts can act as a resistor as well. Thirdly, the metal contacts will have a resistance as well. How does the series resistance appear in an electric circuit? Here we'll use a zigzag line as a symbol for the resistor. Note that sometimes a rectangle is used as a symbol for resistor as well. As discussed earlier, the ideal solar cell is a parallel connection of a current source and a p-n diode. The series resistance is, as the name already reveals, connected in series with these two elements. If the solar cell generates current, the solar cell will lose voltage over the series resistance. The second resistance is the so-called parallel resistance, or also referred to as the shunt resistance. A shunt is a macroscopic defect in the solar cell which provides an alternative path for the generated photocurrent. Examples of a shunt are a crack through the semiconductor layers or a current path at the edge of the solar cell. In the electric circuit, the shunt resistance appears as a resistor connected in parallel with the current source and the diode. A low shunt resistance means that a large fraction of the photocurrent prefers to travel through the shunt, while a high shunt resistance means that less or no photocurrent is lost through the shunt. Important to remind is that you would like to have the series resistance as small as possible and the shunt resistance as large as possible to come close to an ideal illuminated p-n junction. The series and shunt resistance results in a more complicated expression for the JV curve. The voltage at the terminal is the voltage of an ideal solar cell minus the voltage lost over the series resistance. The total current is the photocurrent density minus the dark current density of the diode and the current density leaking through the shunt resistance. The shunt current is given by the voltage of an ideal solar cell divided by the shunt resistance. This results in the complex expression shown here. The current density J appears on the left-hand side of the equation as well as on the right-hand side. Note that this expression cannot be solved analytically. How do the series and shunt resistance affect the JV curve and the fill factor? Let's start with the JV curve of an ideal PN junction as shown in this figure. Now we are going to increase the series resistance. As you see, the slope around the open circuit voltage point starts to become less steep. The larger the series resistance, the less steep the slope will be. Furthermore, the maximum power point is affected as well by increasing the series resistance. The larger the series resistance, the smaller the maximum power point will be. This also implies that the larger the series resistance will be, the smaller the fill factor. In conclusion, the series resistance can affect the fill factor and has to be as small as possible for high fill factors. Note that the series resistance does not affect the position of the open circuit voltage. As at the open circuit voltage, the current density is equal to 0, the voltage drop over the series resistance is 0 as well. Let's start again with the JV curve of an ideal PN junction. This means that the shunt resistance is infinite large. Now we are going to decrease the shunt resistance. As you can see, the slope at the short circuit current density point starts to become more positive. The maximum power point and fill factor is affected as well. The smaller the shunt resistance, the smaller the fill factor will be. Let's look in more detail to the slopes in a JV curve. The slope is current density divided by voltage, which is equal to 1 over the resistance. In this week's homework, we have included an exercise in which you have to prove that the slope at the open circuit voltage point is equal to 1 divided by the series resistance. The smaller the series resistance, the larger the slope and the fill factor will be. The slope at the point corresponding to the short circuit current density in a JV curve is 1 divided by the shunt resistance. The larger the shunt resistance, the closer the slope will be to 0 and the larger the fill factor will be. In summary, the real solar cells and panels have series and shunt resistance. And in solar cell design and manufacturing, it is important to minimize the series resistance and to make the shunt resistance as large as possible. The JV curve of a solar cell has a power density which is varying with voltage. What will determine at which JV point the solar cell will be operating? This is determined by the load which is connected to the solar cell. If the load has a low impedance, the current density will be high and the voltage will be low. It means that the solar cell is not operating in its maximum power point. Whereas if the load has a high impedance, the voltage will be high and the current will be low. Again, the solar cell is not operating in its maximum power point. This means that we need to tune the impedance of the load to have the solar cell working in its maximum power point. If we discuss PV systems later in this course, we will talk about maximum power point trackers. These are electronic devices which varies the load in time such that the solar panel is always working in its maximum power point, such that the maximum amount of electrical power can be generated by the solar panel. So far, we have discussed the external parameters of an ideal and non-ideal solar cell this week. The remainder of this week, we will discuss how these external parameters are affected by the design of the solar cell. I will introduce you general design rules for solar cells. These design rules will help you to understand the performance of the different PV technologies which will be discussed in the coming 3 weeks. In the last 2 weeks, we have discussed the working principle of a solar cell and the external parameters that define the performance of a solar cell. Now, we are going to look at how various solar cell concepts and photovoltaic materials affect the performance of a solar cell. For that, we have to look at some general design rules for solar cells. I always like to show this simple diagram to my students, which summarizes the important design rules. As you can see, I identify 3 important design rules: utilization of bandgap energy, spectral utilization, and the last engineering tool, which is light trapping. First, the real energy used to generate voltage is the product of the open circuit voltage and the elementary charge. Under normal operation condition, this energy is always smaller than the total bandgap energy. Open circuit voltage is determined by the extent to which the quasi-Fermi levels are able to split, which is limited by the charge carrier recombination mechanisms. We will show that the various PV materials have different recombination mechanisms that limit the utilization of the bandgap energy. Secondly, we look at the spectral utilization. The spectral utilization is first determined by the choice of materials which make the solar cell. We will discuss that the bandgap of the materials determine the maximum current density generated by the solar cell. Thirdly, if we have chosen our PV material, its potential utilization of the solar spectrum and its utilization of the bandgap energy, we would like to absorb as much as possible light from the solar spectrum in the PV active materials. We have to implement tricks to trap the light in the solar cell. This becomes an important issue if you consider thin film PV technologies. First, we start with the design rule, the bandgap utilization. Here you see a PN junction. On the left, the p-doped, and on the right, the n-doped. Further, we see the quasi-Fermi levels. The extent of splitting between the quasi-Fermi levels determines the open circuit voltage. Earlier this week, we have deduced an expression for the open circuit voltage, which is shown here. The open circuit voltage depends on the irradiance and the diode leakage current in the dark. This equation can be expressed in terms of the generation rate G, lifetime tau of the minority charge carriers, and the intrinsic density of the charge carriers of the semiconductor material. As the derivation of this equation is out of the scope of this lecture, we have included it as an exercise in this week's homework. The equation tells us 2 important aspects of the open circuit voltage. If we increase the irradiance, or in other words, the generation rate of charge carriers, the open circuit voltage is increased. This is a welcome effect which is utilized in concentrator photovoltaics, which we will discuss later this course. Secondly, we see that the lifetime plays an important role. The larger the lifetime of the minority charge carrier, the larger the open circuit voltage can be. Or in other words, the longer the lifetime, the larger the splitting between the quasi-Fermi levels is possible and the larger fraction of the bandgap energy can be utilized. The lifetime of the minority charge carriers is determined by the recombination rate. As discussed last week, we have 3 different recombination mechanisms: radiative, Auger, and Shockley-Reed-Hall. Let's start with the last one, Shockley-Reed-Hall recombination. The origin of this mechanism is the trapping of the mobile electron at defects that have an energy state in the bandgap. The electron is trapped until a mobile hole finds the electron. after both charge carriers recombine. Shockley-Read-Hall recombination depends logically on the defect density. In the simplest approximation, the minority charge carrier lifetime is reciprocally dependent on the defect density Nt. This means the larger the defect density, the shorter the lifetime, and the smaller the open circuit voltage. The defect density limits the extent to which the quasi-Fermi levels can be split. Defects can be located in the bulk of the various semiconductor materials, but can also be present at the various interfaces between materials used in the solar cell, like semiconductors, transparent conductive oxides, and metal contacts. Let's consider solar cells without bulk and interface defects. Then the other two recombination mechanisms start to play a role. Let's consider Auger recombination. Auger recombination is the process in which the momentum and energy of two recombining hole and electron is conserved by transferring energy and momentum to another hole or electron. This electron is excited in higher levels in the electronic band. This excited electron relaxes again such that the energy is lost as phonon modes. Phonon modes are lattice vibration and is nothing different than heat. As the recombination process is a three-particle process, the Auger recombination rate expressed in R is strongly dependent on the charge carrier densities. N is the density of electrons and P is the density of holes. The R electron is dominant when the electrons are the majority charge carriers, whereas R hole is dominant when the holes are the majority charge carriers. In a simple approximation, the lifetime is 1 over the density of charge carriers squared. As a consequence, Auger recombination becomes dominant in photovoltaic materials with high densities of charge carriers, like in highly doped crystalline silicon, or solar cells under strong illumination, like concentrator solar cells. The last recombination mechanism is radiative recombination. In the three recombination mechanism, energy and momentum are transferred from charge carriers to phonons or photons. The efficiency of these processes depends on the nature of the band gap of the semiconductor material used. Last week I have introduced the physical principle of the band gap. However, I did not discuss the difference between a direct or indirect band gap. I will explain the nature of both types of band gap now. For that we have to look in the energy momentum space of the electrons. On the vertical axis we have the energy state in the electronic bands. On the horizontal axis we got the momentum of the charge carrier. This momentum is also called the crystal momentum. Important to realize is that the position of the valence and conduction band may differ in different directions of the lattice coordination. For indirect band gap, the highest point of the valence band is not aligned with the lowest point of the conduction band. This means that exciting an electron from the valence to conduction band requires energy provided by a photon and momentum provided by a phonon. In contrast, a direct band gap has the highest point of the valence band vertically aligned with the lowest point of the conduction band in the energy momentum space. This means that exciting an electron from the valence to conduction band requires only the energy provided by a photon without any additional momentum transfer. This means that the excitation of an electron induced by photon absorption is more likely to happen for direct bandgap materials than for indirect bandgap materials. For direct bandgap materials, no additional matching momentum coming from phonons has to be delivered. Or in other words, the absorption coefficient for direct bandgap materials is significantly higher than for indirect bandgap materials. The same concept makes the reverse process of radiative recombination more likely to happen in a direct bandgap material. In an indirect bandgap material, additional momentum is required to make the electron and hole recombine. Crystalline silicon is an indirect bandgap material. If we ignore Shockley-Reed-Hall recombination by defects, the radiative recombination in an indirect bandgap material like crystalline silicon is inefficient and recombination will be dominated by the Auger mechanism. For the direct bandgap material as gallium arsenide, under moderate illumination condition, radiative recombination will be the dominant loss mechanism of charge carriers. For very high illumination condition, Auger recombination starts to play a role as well. If we now go back to the open circuit voltage, it means that in defect-rich solar cells, the open circuit voltage is limited by the Shockley-Reed-Hall recombination. In defect-free solar cells, based on indirect bandgap materials, the open circuit voltage is limited by Auger recombination. In defect-free solar cells, based on direct bandgap materials, the open circuit voltage is limited by the radiative recombination. Next to the bandgap utilization, I would like to discuss the relation between the maximum thickness for the absorber layer of a solar cell and the recombination mechanism as well. The recombination mechanism, as we have discussed last week, also affects the diffusion length of the minority charge carrier. The diffusion length is given by the simple equation L, which is the square root of the diffusion coefficient d times the lifetime tau of the minority charge carrier. This leads to one additional limitation of the solar cell design. The absorber layer of a solar cell cannot be thicker than the typical diffusion length. Why is that the case? This is demonstrated in this simple animation. Let's consider photons that would penetrate far into the absorber layer before they are being absorbed. We want these charge carriers to be separated at the p-n junction or the back contact. But let's assume that these charge carriers are excited at a depth deeper than the typical diffusion length. The excited charge carriers recombine within the typical diffusion length before arriving at the p-n junction. In other words, their lifetime is too short. This means that all charge carriers generated at a depth greater than the diffusion length from the p-n junction cannot be collected. If the charge carriers are generated at a depth shorter than the diffusion length, they can be collected. This means that the diffusion length of the minority charge carrier limits the maximum thickness of the solar cell. Summarized, the open circuit voltage is limited by the dominant recombination mechanism. The dominance of radiative, Auger or Shockley-Reed-Hall recombination depends on the type of semiconductor materials integrated into the solar cell and the illumination condition. In the coming weeks, I will give various examples of various PV technologies. In the next block, I will discuss the second design rule, spectral utilization. We answer the question of how much current density can we generate with a certain semiconductor material. We discuss the second design rule, spectral utilization. How is spectral utilization determined? We will discuss this in the coming two blocks. Let's consider a single junction solar cell in which the absorber layer is a material with a certain bandgap energy. We know that when the energy of a photon is smaller than the bandgap, it's lacking the energy to excite an electron to the conduction band. When the energy is larger than the bandgap, absorption of the photon results in a mobile electron and hole. Let's see how the bandgap affects the open circuit voltage and short circuit current density. In this illustration, the conduction, valence band and bandgap of the absorber material are shown. In addition, I represent the solar spectrum by arrows with various lengths and colors. The blue arrows correspond to energetic photons. Their photon energy is much higher than the bandgap. The green and red arrows correspond to photons with lower photon energy. The red photons have a low energy. It's even smaller than the bandgap energy. Note that in this illustration the band gap is relatively large. Only the blue and partly the green photons are able to excite charge carriers. If we look to the JV curve, this is indicated by a relatively low short-circuit current density, while due to the large band gap, a higher open circuit voltage can be obtained. If we now consider an absorber material with a lower band gap, we see that more photons in the spectrum can excite charge carriers. This material will result in large short-circuit current densities. However, due to the smaller band gap, the splitting of the quasi-Fermi levels and the resulting open circuit voltage will become smaller. This is reflected in the blue JV curve. The JV curve of the solar cell with the low bandgap material has a larger short-circuit current density, whereas the open circuit voltage is smaller. An important conclusion of this simple exercise is that the choice of semiconductor material determines the open circuit voltage and the short-circuit current density through its bandgap. Now we are going to look in more detail how spectral utilization of a solar cell can be determined and measured. For that, we introduce the external quantum efficiency. Here we see a solar cell. Let's consider a certain amount of photons at a certain wavelength which are incident on the solar cell. These photons will generate electrons collected at the terminals. The external quantum efficiency is the number of electrons collected at the terminals per incoming photon at a certain wavelength. Not every photon incident on a solar cell will result in electrons collected at the contacts. Lower EQE can be attributed to several optical and electrical loss mechanisms for charge carriers. For example, photons can be reflected back from the solar cell. Photons are not absorbed as they have an energy smaller than the band gap. The absorber layer is too thin and does not absorb all photons. Parasitic absorption losses in the inactive PV layers of the cell. And recombination of the light-excited charge carriers before they are collected at the contacts. Let's say we have a material with bandgap E gap. The ideal external quantum efficiency would look like this graph. Note that the horizontal axis is plotted in wavelength. Smaller wavelengths correspond to higher energetic photons, the blue spectral part. Longer wavelengths correspond to lower energetic photons, the red spectral part. Above the bandgap, all photons result in a collected electron, or in other words, the EQE is 1 or 100%. In reality, the EQE is always smaller than 100% and its value varies with wavelength. EQE spectra are measured using an EQE setup, also called spectral response measurement. I won't go in detail, but such setup needs a wavelength selective light source, a calibrated light detector and a current meter. A xenon lamp is a standard light source used in EQE setups, as it emits photons in the same spectral range of interest of the solar spectrum. Using filters and a monochromator, only light with a narrow band of photon energies is incident on the solar cell. First, using a calibrated detector, the numbers of photons per narrow wavelength band can be determined. Secondly, the current density generated by the solar cell is measured with the same photons incident on the cell. In this procedure, the number of collected electrons and the number of photons per wavelength are measured and the EQE can be determined. If we perform this measurement under short-circuit conditions, the short-circuit current density can be determined out of the spectral EQE. The advantage of measuring the short-circuit current density using an EQE setup above that of the earlier discussed JV measurements is that the current density measured by the EQE setup is independent of the spectral shape of the light source used. Secondly, on lab scale, the real contact areas of solar cells is not accurately determined. The EQE measurement setup, when using shading masks, is independent on the contact area. Let's go to the PV lab to see a typical measurement of an EQE setup. This is an example of a home-built EQE setup which is used to measure the spectral response of small lab-scale solar cells. Here we see the xenon light source and the monogrammeter. To demonstrate the operation of the monogrammeter, we are going to look at the light output which is incident on a piece of paper in the dark. Here you see a condition in which only a narrow wavelength range in the blue light is incident on the paper. Now we move from blue to green light and now from green to red light. We are going to measure a solar cell. This means we first have to calibrate our light source. For that, we use a calibrated silicon photodiode. This means that we can translate very accurately the light-induced currents in the photodiode to the number of photons. The photodiode signal is measured as a function of the wavelength. After calibration of the spectrum power density function of a light source, we repeat the same measurement with a solar cell. As example, we use a crystalline silicon wafer-based lab-scale heterojunction solar cell, which will be discussed next week. The solar cell is positioned at the same spot as the calibration photodiode. The contacts are connected to the ampere meter to measure the generated current. In this example, we measure the cell under short circuit condition. It means that no additional voltage bias is applied to the solar cell. The external quantum efficiency is measured as a function of the wavelength, and in this movie it is going from the blue to the red. The EQE can also be measured when additional reverse or forward bias is applied to the solar cell. As we will discuss in a minute, the measured EQE in combination with the spectral power density of the AM1.5 solar spectrum gives us the short circuit current density of the solar cell. In this case, the current density of the lab cell studied is 350 amps per square meter, or in a more practical unit on lab scale, 35 milliamps per square centimeters. Important to realize is that if you want to report short circuit current densities of solar cells, you cannot rely on a single JV measurement. They have to be measured using an EQE setup. How do we determine the short circuit current density out of the EQE? Under standard test conditions, the solar spectrum is defined as the AM1.5 spectrum with a total power density of 1000 watts per square meters. The total current generated at a wavelength lambda is the elementary charge multiplied by the product of the photon flux phi at AM1.5 and the EQE. The total short circuit current density can be determined if we integrate over the entire wavelength range. Or, as discussed in week 1, the spectral photon flux equals the spectral power density divided by the photon energy. In this graph, the spectral power density is shown in the red. The blue line represents the theoretical short circuit current density at a wavelength lambda. It shows that up to a wavelength of 2000 nanometers, we could theoretically generate a short circuit current density of 62 milliamps per square centimeters. Let's consider crystalline silicon having a band gap of 1.12 electron volt. This equals a wavelength of 1107 nanometers. Then we arrive at a theoretical current density for crystalline silicon of 44 milliamps per square centimeters. I will show you an example of an easy way to estimate the current density using a simple approximation of the solar spectrum. Here we see the spectral power density of an AM1.5 solar spectrum. I will make a crude simplification. The spectral power density function of a solar spectrum can be roughly approximated with a linear increasing line from 300 up to 500 nanometers and a linearly decreasing line from 500 nanometers up to 1500 nanometers. As discussed in week 1, the area under this triangular shaped spectrum represents the irradiance, which for this case is 900 watts per square meters. This is an excellent agreement with the real value for the irradiance up to 1500 nanometers, determined from the real AM 1.5 spectrum. Let's consider crystalline silicon as absorber layer. Crystalline silicon has a band gap of 1.12 electron volt, which corresponds to a wavelength of 1107 nanometers. For simplicity, we take 1100 nanometers. And we assume that the EQE is 90% above the band gap. Or in other words, 10% of the photons do not result in the collection of an electron. The short circuit current density is the integration over the area of the product of the EQE and the simplified spectral photon flux. If we do this exercise, we arrive at 39.4 milliamps per square centimeters. This is a realistic number if we consider the typical current densities of the best monocrystalline silicon-based solar cells. If we would have an EQE of 100%, we estimate a current density of 43.8 milliamps per square centimeters. This is again in excellent accordance with the theoretical current that crystalline silicon can generate, as we have seen earlier. This provides you an easy tool to make realistic estimations on the possible photocurrents that various materials can generate. In summary, we have discussed how to determine the spectral utilization of a single junction solar cell. The band gap of the semiconductor material determines the theoretical maximum current density and open circuit voltage that can be obtained. In the next block, we will discuss the optimum performance of single junction solar cells under standard test conditions in more detail. For a single junction solar cell, the band gap of the semiconductor material determines the theoretical maximum current density and the open circuit voltage that can be obtained. Therefore, considering single junction solar cells, we arrive at the next question. What is the optimum band gap for the absorber semiconductor at which the highest conversion efficiency can be obtained using the AM 1.5 solar spectrum? Let's find an answer to that question. Here we see the spectral power density function again. Let's consider the typical optical loss mechanism for a semiconductor with a band gap E gap. Again, we take crystalline silicon as an example. Furthermore, we assume an EQE of 100% above the band gap for the solar cell. Let's look at photons with energies higher than the band gap. We know that we effectively only need energy of the band gap to excite the mobile charge carrier. The electrons are excited to a level higher up in the band gap and the holes down to a lower level in the valence band. They will quickly relax back to the edges of both bands. The rest energy is released in terms of heat. The gray area represents the total amount of energy in the solar spectrum which is used to excite the charge carriers. The yellow area above the band gap represents the energy which is lost as heat. All energy present in the solar spectrum below the band gap is not absorbed and can be considered as an optical loss as well. Both loss processes, heating and non-absorption, depend on the band gap. The higher the band gap, the smaller the losses due to heat, but the larger the energy losses below the band gap. The smaller the band gap, the larger the losses due to heat, whereas the energy losses below the band gap decreases. This suggests that if we only consider the optical losses and ignore all other losses, we will have an optimum. The optical losses due to this mismatch between the band gap and the solar spectrum limit the maximum conversion efficiency to 48%. However, this limit is not very realistic. In literature, people generally refer to the so-called Shockley-Queisser limit. This theoretical limit includes two additional loss mechanisms. First, as the solar cell is at a certain temperature, it will act as a black body radiator itself and emit light in the far infrared. This energy loss is roughly around 7% of the incident energy of the AM1.5 solar spectrum. Secondly, we have to consider that we do not fully utilize the bandgap energy for the open circuit voltage. As discussed earlier this week, the maximum open circuit voltage is limited by the recombination of charge carriers. In reality, we can have three charge carrier recombination mechanisms: radiative, Auger, and Shockley-Reed-Hall. In this case of the Shockley-Queisser limit, only radiative recombination is considered. This means, in a very simplified picture, we make a kind of thermodynamic approach of the solar cell. We have the AM1.5 spectrum incident on a solar cell. We don't allow the solar cell to increase in temperature. This means that all energy in the incoming AM1.5 spectrum can escape the system of the solar cell by either the current density generated or by the radiative recombination of charge carriers. In this figure, the energy lost as heat is indicated as excess energy. This means that for a low bandgap material, as shown here, the energy loss below the bandgap is moderate. However, the amount of excess energy of the energetic photons is significant. Due to our restrictions, this energy has to leave the system through radiative recombination. Therefore, radiative recombination is enhanced for low bandgap materials. This means that for a high bandgap material, the energy loss below the bandgap is dominant, and the excess energy determines the amount of charge carriers that radiatively recombine. As a result, we get this following picture. It shows the loss mechanism, black body radiation, relaxation of charge carriers to the bandgap edges, and lost energy below the bandgap. The black part shows the usual energy in single junction solar cells according to the Shockley-Queisser limit. The Shockley-Queisser has an optimum of 33% for bandgaps in the range of 1 electron volt up to 1.5 electron volt. For single junction solar cells, you can see that the semiconductor materials as silicon, gallium arsenide and cadmium telluride have an optimum bandgap. However, if we look at the record efficiencies of solar cells, they are all below the Shockley-Queisser limit. The reason for this is that additional optical losses like reflection, parasitic absorption, and electrical losses like the Shockley-Reed-Hall and Auger recombination are not considered. The Shockley-Queisser limit only considers radiative recombination. Therefore, its efficiency limit is most valid for direct bandgap materials like gallium arsenide. As discussed in the previous block, due to its direct bandgap, radiative recombination is the limiting recombination mechanism for the open circuit voltage of gallium arsenide. Later in this course, we will discuss various concepts which might allow to pass the Shockley-Queisser limit. Here I will give a quick example. A way to reduce the amount of excess energy is to use more than one semiconductor material, or often referred to as a multi-junction. This allows us to use more than one bandgap and the match with the solar spectrum improves. As you can see in this example, the excess energy can be reduced significantly and the spectral utilization improves. We will discuss such multi-junction concepts in greater detail in week 5. So we have discussed the utilization of the solar spectrum and bandgap energy. This week we'll finish with the final 2 blocks describing the third design rule, light trapping. The last engineering tool is light trapping. In the ideal solar cell, we want all light that is incident on the solar cell to be absorbed in the absorber layer. However, nature has not made our life that easy. Let's start with absorption. How does absorption work? Let's consider the simple system of a single absorbing medium with a thickness d. From the left, we have a light ray which is coupled into the film into the x direction. Part of the light is absorbed in the film. Consider x is 0 to be the front side of the medium and x is d is the back side of the medium. At the moment, we make a simplification. First, we neglect the reflection or potential scattering at the interfaces. Secondly, we assume the light is monogrammatic, which means that all photons have the same energy or wavelength. The absorption of a medium can be defined in terms of an absorption coefficient alpha. The dimension of the absorption coefficient is 1 over the length, and the typical unit of the absorption coefficient used is 1 over centimeter. The light intensity drops exponentially with distance in the absorber layer. This behavior can be described by the Lambert-Beers law. This law states that there is a logarithmic dependence between the intensity of the transmitted light through the layer and the product of the absorption coefficient and the path length. Or presented in another way, over an infinitely small distance dx, the decrease in the light intensity due to absorption, di dx, is equal to the product of the absorption coefficient and the light intensity at position x. This is the differential form of the Lambert-Beers law. Lambert-Beers law shows that the light intensity is decreasing exponentially in the x direction of the absorbing medium. It also means that at the site at which the light is entering the film, more light is absorbed in the reference to the backside. The total light intensity absorbed in the material is equal to the light intensity entering the absorber layer minus the intensity transmitted through the absorber layer. For a solar cell, we would like the absorption to be 100%. In this condition, the absorber would be called optically thick. This means the transmission is 0%. From Lambert's law, it can easily be seen that this can be accomplished by either large values for the thickness d, so very thick films, or large values for the absorption coefficients. It is important to realize that the absorption coefficient for materials is not the same at every wavelength. In this figure, the absorption coefficients for 4 different semiconductor materials are plotted: germanium, silicon, gallium arsenide, and indium phosphide. First, you see that germanium has the lowest band gap. Germanium starts to absorb at high wavelengths, which means low photon energy. Gallium arsenide has the highest band gap as it starts to absorb light at the smallest wavelength or the highest photon energy. Secondly, if we focus on the visible spectral part from 300 nanometers up to 700 nanometers, we see that the absorption coefficient of indium phosphide and gallium arsenide is significantly higher than that for silicon. This is related to the fact that indium phosphide and gallium arsenide are direct bandgap materials as discussed earlier. Materials with an indirect bandgap, like silicon and germanium, have smaller absorption coefficients. Only in the very blue part, below 400 nanometer, silicon has a direct bandgap transition. Silicon is a relative poor absorber and therefore thicker absorber layers are required in reference to gallium arsenide to absorb the same fraction of light. In general, all semiconductor materials show that the absorption coefficient in the blue is orders of magnitude larger than in the red. This means that the penetration depth of blue light into the absorber layer is rather small. Let's take as an example the normalized light intensity with position in the silicon bulk. As you can see in this graph, the blue light is already fully absorbed within a few nanometers. The red light requires an absorption path length of 60 microns to be fully absorbed. The infrared light is hardly absorbed, and after an optical path length of 100 microns, only 10% of the light intensity is absorbed. As the absorption of photons generates excited charge carriers, the wavelength dependence of the absorption coefficient determines the local generation profile of the charge carriers. At the front side, where the light enters the absorbing film, the generation of charge carriers is significantly higher than at the back side. It means, if we look at the EQE of a solar cell, the EQE values measured in the blue correspond to charge carriers generated close to the window layer, whereas the EQE in the red part represent charge carriers generated through the entire absorber layer. Now we are going to look at some optical loss mechanism. Let's consider a simple crystalline silicon solar cell. Next week we will focus on this PV technology in more detail. The example of the crystalline silicon solar cell shown in this figure consists of a p-type crystalline silicon bulk with a thin n-type layer on top, referred to as the N-emitter. At the top and the back we have the metal contacts. Using this relatively simplified solar cell configuration, we will demonstrate the various optical losses, or in other words, which mechanism prevent that all light is being absorbed in the p-type crystalline silicon solar cell. First, we consider the metal contacts. These contacts shade a certain area, preventing light to be absorbed in the PV active layers. The second optical loss mechanism is the reflection at the front interface of the solar cell. The light passing through an interface between two media with different refractive indices will always be partly reflected and partly transmitted at the interface. As all types of solar cells suffer from this loss mechanism, I would like to spend some time on this in the next block. I will discuss some concepts which are being used as anti-reflection coatings. A third optical loss mechanism is parasitic absorption losses in the non-active PV layers. In this example, the green top layer can be an anti-reflection coating or a passivation layer to reduce the number of defects at the surface of the emitter layer. If this layer absorbs photons, these photons will not contribute to charge carrier generation that will be collected at the contacts. This is what we address as parasitic absorption. This means that in a design of solar cells, we preferentially would like to use materials for the non-active part of the solar cell that have high transmissions for the spectral part utilized by the solar cell. Finally, if the absorber layer is not thick enough to absorb all light, part of the light will be transmitted. This loss mechanism starts to play a role for solar cells based on thin films. In the next final block of this week, I will discuss methods to reduce the reflection at the front surface of a solar cell, and I will discuss under which condition light might be trapped in the absorber layer. How to reduce the reflection at the front surface of a solar cell and how to increase the light trapping in the absorber layers. I will discuss some general concepts which will come back in many PV technologies, which we will be discussing the next 2 weeks. In the previous block, we discussed the optical loss mechanism due to reflection at the front interfaces of a solar cell. The light passing through an interface between two media with different refractive indices will always be partly reflected and partly transmitted at the interface. As all types of solar cells suffer from this loss mechanism, I will discuss first some anti-reflection concepts. First, I will discuss the physical origin of reflection of light in more detail. The fraction of the light intensity that is reflected is given by the Fresnel coefficient. Consider the interface between two media with refractive index N1 and N2. A light ray is arriving with an angle of incidence in reference to the normal of the interface theta E. Part of the light is reflected on the angle of reflection theta R. The angle of reflection is equal to the angle of incidence. A light ray is arriving with angle of incidence in reference to the normal of the interface theta I. Part of the light is reflected on the angle of reflection theta R. The angle of reflection is equal to the angle of incidence. The light transmitted travels further on the angle of transmission theta 2 to the normal. The relation between the angle of incidence and transmission is given by Snell's law. If refractive index of medium 1 is smaller than that of medium 2, the angle of transmittance will be smaller than the angle of incidence. If the refractive index of medium 1 is larger than that of medium 2, it's the other way around. In this example, the waves represent the electric field oscillations in the plane of incidence. This can be seen as we put this plane in a three-dimensional illustration. This is what we call p-polarized light. The opposite situation is the configuration in which the electric field is oscillating perpendicular to the plane of incidence. This is what we call s-polarized light. The reflection coefficients are given by the Fresnel equations, which are functions of the refractive indices of both media and the angle of incidence and reflection. The transmission is 1 minus the reflection. I'm not going into detail, but the Fresnel equations for transmission and reflection of the p-polarized light are slightly different for that of the s-polarized light. For light where the perpendicular incidence, that is an angle of incidence of 0 degrees, the reflection and transmission are equal. In this graph, you see the relation between the reflection coefficient for S and P polarized light when the medium 1 has a refractive index of 1, which is equal to air, and medium 2 has a refractive index of 1.5, like glass. What we can see is that the P polarized light has an angle at which the reflection is equal to 0. This angle is called the Brewster angle. The gray line is the average, which represents randomly polarized light. If we look at light rays going from a material with a higher refractive index to a material with a lower refractive index, we see that the reflection becomes 100% above a certain angle. This is called a total internal reflection and occurs above the critical angle of incidence, which can easily be calculated using Snell's law. Using these basics, we will look at the interface of silicon, the most common used material for solar cells. Consider an air-silicon interface and, for simplicity, light under a perpendicular incidence at a wavelength of 500 nanometers. This example is included as an exercise in this week's homework as well. The refractive index of air is 1 and that of silicon is 4.3 at a wavelength of 500 nanometers. The Fresnel coefficient tells us that the optical losses due to reflection are significant at this interface. The reflection is 38.8%. Reduction of this reflection can be achieved by introducing an interlayer with a refractive index N1 with a value between that of N0, air, and Ns, that of silicon. Including this interlayer in the system, you can simply work out the effective reflection coefficients from the front side. This is the reflection from the first interface plus the reflection of the second interface. In this first approximation, we do not consider the multiple reflections within the interlayer. We then plot the reflection coefficient of this example versus the refractive index of the interlayer. The blue line is the reference reflection without interlayer. The red line is the reflection with interlayer. The red curve has a minimum. This minimum is exactly at the value equal to the square root of the product of refractive index N0 and N2. In this example, by inclusion of a single interlayer, the reflection at the interface can be reduced from 38.8% down to 22.9%. Using more than one interlayer, also called refractive index grading, this reflection can be further reduced. Another approach of anti-reflection is making use of constructive and destructive interference of light. As we discussed in week 1, light can be considered as electromagnetic waves. Waves have the interesting properties that they can interfere with each other. Waves can be superimposed. As demonstrated in this animation, so in the case of light, the amplitude of electric field of wave A and B at certain position x, y, z at time t are superimposed. It means that the resulting amplitude of a wave A plus B can be larger or smaller than the original wave A and B. When two waves A and B are traveling in the same direction and are in phase, the resulting amplitude is larger than for a single wave. This situation is called constructive interference and is shown on the left. When waves A and B are in antiphase, the amplitude of the resulting wave is equal to 0. This situation is shown on the right and is called destructive interference. One can design an anti-reflection coating based on this principle. Look at this animation. Again, we have placed an interlayer between two media. The green wave shows the reflection back from the first interface, and the red wave shows the wave which is reflected back from the second interface. If we look at the two waves coupled out of this system, they appear to be in antiphase. As a result, the total amplitude of the electric field of the outgoing wave is smaller, and the total irradiance coupled out of the system is smaller as well. The maximum destructive interference occurs when the product of the refractive index and thickness of the interlayer is equal to the wavelength divided by 4. Or in other words, the thickness is the wavelength divided by 4 times the refractive index of the coating. Using an anti-reflection coating based on interference means that the typical length scale of the interlayer thickness must be in the order of the wavelength. A last and completely different approach for anti-reflection is using textured interfaces. The length scale of the textured features is larger than the typical wavelength of light. The reflection and transmission of the light rays are determined by the Fresnel equations and Snell's law. The texturing helps to enhance the coupling of light into the layer. For example, for light that is perpendicular incident, light that is reflected at the textured surface can be reflected at angles in which the trajectory of the light ray is incident somewhere else on the interface. Here, part of the light will be transmitted into the layer and effectively less light will be reflected in reference to a flat interface. Summarized, we have discussed 3 types of anti-reflection approaches: a Rayleigh film, anti-reflection coating based on destructive interference, and enhanced incoupling of light due to scattering at textured interfaces. Secondly, if the absorber layer is not thick enough to absorb all the light, part of the light will be transmitted. As the absorption coefficients are larger in the blue spectral part, this usually plays a role in the red to infrared part of the solar spectrum. The light transmitted can be reflected back, which is a so-called back reflector. Some of the light can also be absorbed at the back contact. This can again be considered as a parasitic absorption loss. In week 5, we will discuss thin film solar cells, where back reflectors and light scattering on the angles starts to play an important role. For these type of solar cells, you would like to scatter light under the critical angle. I will explain the importance of the critical angle right now. Consider a single film of absorber material with a higher refractive index than its surroundings. For some magic reason which we for the moment ignore, the light scatters under a certain angle into the film. The light is scattering between the two interfaces, down and up. In the ideal case, you would like to have all light trapped in the absorber layer, making the absorption path length so long that all the light is absorbed. Unfortunately, at every internal reflection, part of the light is transmitted out of the film. However, this is not the case when there is a total internal reflection. From the Fresnel equations, we know that above a critical angle, the internal reflection becomes 100%. This means that if the light is scattered into the film above a critical angle, the light would be trapped. The critical angle is a function of the refractive index of both media. If we consider silicon and air, this critical angle is rather small, 13.4 degrees. However, absorber layers are usually confined between supporting layers. If we would consider glass with a refractive index of 1.5, the critical angle becomes 20.4 degrees. If we consider zinc oxide, a typical transparent conductive oxide, we find a critical angle of 30.3 degrees. In the coming weeks, we will discuss various tricks to scatter the light on the angles into the absorber layer. Here you can see an example of scattering at microscopic texture, which enhances the absorption path length into the absorber layer. Summarized, this week we have learned some important concepts. We have discussed how we determine the performance of a solar cell using the external parameters. In addition, we have discussed some important design rules for solar cells. Next week, we shall discuss the most dominant PV technology in the market, crystalline silicon. So, see you next week.